Okay, so in this video, we're going to be talking about something we'll need in some future videos, and that is a particular limit of a complex exponential function. Okay, so I'll just leave it at that. We're going to be talking about a specific limit of a complex exponential. So first, let me just write out a complex number z, and I'm going to use these symbols, okay, which are going to play a role in the future topic of Laplace transforms. So I'm just going to write z as sigma, which is the real part of z, plus j times omega, which is the imaginary part of z. And so z is a complex number. That's what this means, is an element of a set of complex numbers, and sigma and omega are real numbers. Okay, so that's just a plain old complex number z, and I'm just denoting the real and imaginary parts by these symbols because, like I said, we're going to use that in future videos. And what we want to consider, okay, is the function, the complex exponential function, e to the z times t. Okay, e to the zt. Okay, and we want to look at what happens particularly as t goes to infinity. Okay, so what happens here? So let's talk about that. So the limit as t goes to infinity of e to the zt. Well, I know what z is. Okay, z is just sigma, the real part, plus j times omega, the imaginary part, times t. Okay, and I can split up that exponential. So that looks like e to the sigma t times e to the j omega t. Okay, so what can we say about these two functions? Well, this one right here, sigma is real, t is real, e is real, so this whole thing is real. And over here, this is the complex part. Okay, so we're going to look at each one of these parts. Let's just start with the complex one. So let me just make a note here. The magnitude of this, right? As t is any number, when t is any number, this is just a complex number in polar form, e to the j times some real number, right? Because omega is real. And so that's just a complex number in polar form with magnitude 1. The magnitude of that is always 1 for all t. Okay, so what it looks like as t increases in the complex plane, imaginary part, real part. Okay, if omega happens to be positive, then it's just going to go around and around and around the unit circle that direction. If omega is negative, it's going to go around the other way. Okay, but in any case, the magnitude is always 1. And that complex number is always somewhere on the unit circle. Okay, so as far as the limit as t goes to infinity is concerned, what we're really going to be talking about here is when does this converge to something? When does it go to infinity? Or can it ever not even have a limit? And the point is this part over here has magnitude 1 always. That's not going to help us with convergence. The part that's going to help us with convergence is this real part. So for this thing to converge, what would I want to have happen? I don't need the arrow, you guys see it? What would I want to have happen? Okay, well, I would want this real part to get really small, right? I would want sigma to be negative. So that is a decaying exponential. So as t goes to infinity, this gets really small. This is just staying with magnitude 1. So when I multiply them, I'm going to get something really, really small, and eventually it's going to go to 0. Okay, so that's our first case. We get 0, and this is if sigma is negative. The real part is negative. And what does it look like in a picture? In a picture, remember, this is our part that deals with the angle, right? This is the magnitude, and this is e to the j times the phase. So that's going to be spiraling around, and this thing's going to keep getting smaller in magnitude. So together, they're going to combine to kind of do this inward spiral thing, and eventually it gets to 0. Okay, what happens if sigma actually equals 0? What happens then? Okay, well, if sigma equals 0, then this is just 1. And so 1 times this complex number, that's just going to stay going around and around the unit circle forever. All right, let me actually give myself a little more space here. Okay, so if sigma is 0, what's going to happen in the complex plane? It's just going to keep spiraling around with magnitude 1 forever. It never converges to anything. It never converges to anything at all. Okay, so that limit is actually undefined. Okay, it doesn't converge to anything at all. And what happens if sigma is positive, the last case? Well, then it's going to be similar to the first case, but instead of spiraling inward, we're going to spiral outward. Okay, so it starts spiraling out of control, and so that limit is going to infinity, and by infinity, I just mean that it's spiraling outward. Spiraling outward. Okay, so let me just summarize everything. Okay, let me give myself just a tad more room. Shrink that down a little bit. Okay, so what do we need to get convergence if we ever encounter e to the some complex number times t? Well, as long as the real part of z is negative, that implies that e to the zt goes to 0 as t goes to infinity. Okay, and that's what we're going to need. So we're going to encounter terms that look like e to the some complex number times t, and we want to be able to say, okay, based on this video, if the real part of that thing multiplying t is negative, then that complex number goes to 0 as t goes to infinity. Okay, so that's something we're going to be using in future videos, and this is the explanation for it. All right, that's all I have for this video. I'll see you in the next one.